In our earlier lectures, I have stated that the molecules in a gas are moving at random in all directions with equal probability, and this is the isotropic nature of this molecular motion. So now, whenever the gas have been kept in a vessel or in a container at equilibrium, means at constant temperature and at a constant pressure, the molecules, while they are moving at random, there are two types of collisions. One is wall collisions, that means molecules are colliding with the wall of the container, and other is the molecules are colliding with themselves, and former is called the wall collision, and this is later we call the intermolecular collisions. So collisions will be of two types. Suppose the gas have been kept in a container. Suppose this is the container, and the molecules, these are the molecules are not at rest. They are moving always at random motions. So molecules they are colliding with this wall of the container, and this is called the wall collision. And also the molecules are colliding with themselves. These are called the intermolecular collisions. By means of a frequency of the molecular collisions, we know the collisions made by the molecules in unit time. So today we shall confine our discussion in the frequency of wall collisions. In my next class, I will go for the frequency of intermolecular collisions. So, actually, in case of wall collisions, we consider the frequency of wall collisions means the collisions made by the molecules on unit area of the wall in unit time. So this is called frequency of wall collisions. I will say ZW called the frequency of wall collisions, means how many molecules are striking unit area of the wall in unit time. In CGS system, unit area may be taken centimeter square and unit time second. In SI system, the unit area may be taken as a meter square, and time is always taken in second. So we like to express, we like to find an expression of frequency of wall collisions in a gas, in a particular gas, confined in a vessel at equilibrium with this temperature and pressure. So this type of expressions we can do in two ways. One is approximate estimate of the frequency of wall collisions, and other is a very accurate one using the Maxwell's distribution of molecular velocities. So first we go for approximate calculations. Approximate estimation of ZW is a very approximate. Suppose this is 1. This is 1, and suppose this is unit area. Unit area of the wall. We like to find out the expressions of how many molecules are striking this unit area of the wall in unit time. So we may consider a cylinder. Consider a cylinder of length, the average speed of the molecules. Suppose we are considering this is the cylinder, and the length of the cylinder is c bar, average speed. Means the c bar distance. This is the distance travelled on an average by a molecule in unit time. So the molecules which are within the distance c bar, they can strike this wall. But the molecules which are having the distance greater than c bar, that means says here, these molecules cannot reach the wall in unit time. The molecules which are at a distance less than c bar, here, they can easily go to the wall and can strike the wall. So this is the cylinder, and this cylinder we can call the heat cylinder. And the molecules within the heat cylinder may have the chance to strike this unit area. Say volume of the cylinder is equal to c bar into 1. 1 is the area of cross section. 1 is the area of cross sections of this wall. If we consider the n dash is the number density, number density of the molecules in the gas at a temperature T and pressure P, then the number of molecules present within this heat cylinder is number of molecules present in the heat cylinder is equal to c bar into 1 into n dash. Number density means the number of molecules of this gas per unit volume. So this is the total volume of this cylinder. So n dash whenever multiplied by C dash into 1, it will give you the total number of molecules present within this cylinder. But you must not think that all the molecules within this cylinder will hit this unit area. Molecules are moving in all directions with equal probability. So total directions we can assume there are 6 directions. Say this is one direction, this is another direction, this is another direction, this is another direction, this is another, this is another. So there will be the 6 directions equally probable for the molecules to move. So in a particular direction, the molecules will move 1/6 of this number. So actually Z, which is called the frequency of collisions, is equal to 1/6 n dash C bar. This 1/6 is the probability of a molecule to move along this direction to hit the wall of the wall, to hit the unit area of the wall in unit time. This one generally written as alpha into n dash C bar. Alpha is the probability for the molecule to move in a particular direction. If we go on in accurate estimation, accurate calculations, accurate expression using the Maxwell's distribution law, then this alpha will be equal to 1/4. 1/4, and this could be done by the following way. Accurate expression of ZW. Accurate expression of ZW. This could be done easily by means of this Maxwell distribution of the molecules in one dimension. Suppose this is the x-axis. This is the x-axis. This is origin. And this is the x component velocity. This is the plus infinity and this is minus infinity. This is minus infinity, plus infinity. The minus infinity to plus infinity is the range of this x component velocity u. This is origin. Let us consider a wall placed perpendicular on the x-axis in the side 0 to plus infinity. So suppose this is the unit area of this wall. Unit area of the wall placed perpendicular along this x-axis in the range 0 to plus infinity. So u the velocity Here u the velocity since the molecules are moving in a particular direction. So the molecules that can come and strike this wall must be from this u distance. U the distance travelled by the molecule in unit time. So the number let dn dash is the number density of the molecules moving in this particular direction, moving in the preferred direction along x-axis with velocity u in the range 0 to plus 0 to plus infinity. So dn dash is the number of molecules per unit area of this gas at a given temperature, pressure, which are moving in these directions with the along this x-axis with the x component velocity u in the range with velocity u in the range 0 to plus infinity. The molecules which are moving along this x-axis with limit 0 to minus infinity, they are moving in wrong direction, and these molecules cannot strike the wall which is placed here on the perpendicular on this x-axis in the range 0 to plus infinity. So these molecules, the molecules are having the velocity 0 to minus infinity cannot hit this wall. So actually, say n dash is the number density. Number density of the molecules. Number density of the molecules in this gas at a given temperature and pressure. So this is the total number of molecules per unit volume, and this is the number of molecules that will have the certain possibility to strike this wall of the unit area of this wall placed perpendicular on this x-axis in the range 0 to plus infinity. We know that dn dash by n dash equal to a into e to the power minus b u square and dE. This is the Maxwell distribution law along this one-dimensional motion. So A is constant, A, B, these two are the constants. Depends on the nature of this gas, but does not depend on the x component velocity u. This is the fraction of the molecules having the velocity u to u plus du, but the range will be 0 to plus infinity. So actually this dn dash equal to n dash A into e to the power minus bu square and du. This is the number of molecules. This is the fraction of the molecules per unit volume. This is the number of molecules in this gas per unit volume, which can strike this wall of the wall placed perpendicular to the x-axis. So this ZW, frequency of wall collisions, will be integrated 0 to plus infinity. 0 to plus infinity. Having the velocity u to u plus du. And the volume is u into 1 and the n dust. So this is equal to 0 to infinity and u, and instead of dn dash we can write this n dash a in the power minus bu square du. This is the number of molecules. This is the number of molecules that will strike this wall, unit area of this wall in unit time. All possible range of this u have been taken. 0 to minus infinity range is discarded, neglected, not taken, as this is the wrong direction for striking this wall. If here is the wall, then we can, if we like to strike this wall, then we can have to go in this way. If we go in this direction, so then I have no chance to hit this wall. So this is equal to a n dash 0 to infinity u e to the power minus bu square and d. And we all know the a equal to root over of b by pi, and b equal to m by 2 kT. M by 2 kT. M the molecular mass of this gas and T the temperature. And this integration we can do more easily by using this gamma function. Gamma function here u equal to n equal to 1. Whenever n equal to 1, so this integration, this ZW is equal to, instead of b we can write b by pi here into n dash into this one n equal to 1, so gamma 1 divided by 2b, that means gamma 1 by 2b. This will be the delta. Now gamma 1 equal to 1. So we can go here. This n dash is the number density, number of molecules per unit volume of this gas at a given temperature pressure, and this one into root over, say, and here this square, here it is 4, 1 by 4 pi b. Pi is there, and b root over b, and 2 whenever included in square root, it becomes 4. Now this if we put this value of b, then it will be n dash into root over of 4 pi and b this one. So 2 kt will go up, 2 kt will go in the numerator, and it is 4 pi n. This can be arranged in this way. If we keep here 1 by 4 into n dash, then it will be root over 2 kt by, here it is 16, 4 is to be multiplied here also, then 4 whenever included in this root over, then it is 16 and 4 pi n. This is equal to 1 by 4 n dash, and this 4 root over of 8 kt by pi n. This is the value of Z, accurate value. And 8 kt by pi n, we know it is the average speed of the molecules. So here the alpha becomes 1/4, and this is equal to 1/4 n dash c bar. However, this integration we also could do by taking the b u square equal to z, then b u square equal to z, or twice b u du equal to dz. Then put here and you do the integration, and the integration will come up the same value with the as we have done by using this gamma function. Gamma function is a very shortcut way to integrate, to have the value of the standard integrals. So this is a very accurate value of this ZW. 1 by 4 into n dash c bar. We can do one problem. Say problem number 1. Problem 1. Based on this expression. Say calculate the number of wall collisions. Calculate the number of wall collisions. Calculate the number of wall collisions per square centimeter per second of oxygen gas at 25 degrees centigrade and 1 atmosphere pressure. We must have to know the temperature and pressure, otherwise this n dash could not be calculated. N dash depends on the pressure and temperature of this gas. This has been Calcutta University set in Calcutta University 2010. This is a problem. So if we use this one, ZW solution, ZW equal to 1 by 4th N dash CR, and N dash equal to N dash, you know the number density of the gas, number density of the molecules in this gas at this temperature T, temperature 25 degrees centigrade, pressure 1 atmosphere. This could be obtained from this ideal gas PV equal to nRT, or we can write N is the number of moles of this gas. Number of moles, we can write this total number of molecules divided by the Avogadro number into RT. Or we can write P equal to N by V. V is coming here, and into RT by N dash. N is the Avogadro number. So this is the total number of molecules of this gas. This is the total volume. So total number of molecules by total volume will give you the number of molecules per unit volume. So this will be equal to N dash into RT by Avogadro number. So actually N dash equal to P into Avogadro number divided by R into T. If we put the values here, instead of P we can write 1 atmosphere, and instead of Avogadro number 6.023 into 10 to the power 23, and molecules mole inverse molecules mole inverse, and divided by R equal to R. If you like to, this problem have been given in CGS system. So R would be expressed in terms of Cc, atmosphere, mole inverse, Kelvin inverse. So it is 82 Cc, atmosphere, mole inverse, Kelvin inverse, and T equal to 25 degrees centigrade means 298 Kelvin. So all the data have been inserted, and you can cancel the units: mole inverse, Kelvin inverse, and this will give you the value. And this value comes up 2.465 into 10 to the power 20, 10 to the power 19, 10 to the power 19, and this is the molecules per cc. Cc is the unit volume here. So this N dash we have calculated, and this is 2.465 into 10 to the power 19 cc molecules per cc. Now this is C. Now this is C bar. This is the average speed. Average speed of the molecules, and this is equal to root over of 8 RT by pi L. If we write the R is molar gas constant, M the molar mass of this gas, and this is equal to root over of 8 into, here the R is to be substituted in terms of arc mole inverse Kelvin inverse, otherwise the unit will not be coming. This must be it has average speed, must have the unit centimeter per second. So actually R equal to 8.31 into 10 to the power 7 R mole inverse Kelvin inverse into temperature 298 Kelvin, and divided by pi equal to 3.14 into M equal to 32 gram mole inverse. This value mole inverse cancel, Kelvin inverse cancel, and arc per gram, root over arc per gram, if we do as we have done previously, it will give you the unit centimeter per second. So this value, this C bar will come up 44403. 4403 centimeter and second inverse. You can do root over arc by gram will give you the centimeter second inverse. Now if we put here this ZW, this 1 by 4 into N dash equal to 2.465 into 10 to the power 19 into 19 molecules centimeter inverse 3 into this 44403 centimeter second inverse. So if we multiply this 2, it will give you the 2.74. It will give you 2.74 and it will give you the 2.74 into 10 to the power 23. 10 to the power 23 molecules. Here centimeter inverse 2 and second inverse 2. So this is the number of molecules that will strike unit area, a 1 square centimeter area in 1 second time. So this is ZW. Now if we like to calculate how much the mass of this gas striking unit area in unit time. This is a very valuable calculations. Suppose we are the human body standing here, then we can calculate how many oxygen molecules or how many nitrogen molecules are, what are the mass of this oxygen or nitrogen molecules that will strike on the surface of our human body. So actually this if we denote this mu, mass of the gas striking unit area in unit time, then this will be equal to this ZW into mass. This is the number of molecules striking and M is the molecular mass. This means mass of each molecule. So number of molecules when you are multiplied by this mass of each molecule, it will give you the total mass. So this will give you the 1/4 and N dash M into C bar. And you see this one, N dash is the number of molecules per unit volume and M the mass of each molecule. So product of these two will give you the density. Mass of this gas per unit volume means mass density. So this this mu can be written as 1/4 rho into C bar. Rho the mass density means amount of this mass per unit of volume of this gas. Here also I can give a simple problem. Problem 2. Problem 2. The average speed of hydrogen gas molecules is 2 into 10 to the power 5 centimeter second inverse at temperature T. Temperature T. Calculate the number of grams. Calculate the number of grams of hydrogen gas striking one square centimeter in 1 second. Condition is such that molar volume of the hydrogen gas is 1 liter. Very simple problem. We have the formula, this mu equal to 1/4 and rho into C bar. Now, the condition is such that the molar volume of the hydrogen gas is 1 liter. That means molar mass of this hydrogen gas is 2 gram per mole. And 2 gram per mole is occupying 1 liter, means 1000 cc in this container. So actually this rho equal to 1/4 into rho, we can write this 2 gram mole inverse m by v. Rho equal to m by v. Molar mass divided by molar volume. Molar mass of this hydrogen is 2 gram mole inverse and volume is 1 liter, means 10 to the power 3 centimeter cube. And the C bar is 2 into 10 to the power 5 centimeter second inverse. This is the solution to this problem. So here 2 and 2, here 4 will cancel out, and here also mole inverse, 1 liter per mole. So this mole inverse cancelled, and so this will give you 4 to 2 only 100 centimeter, 100 gram centimeter inverse to second inverse 1. That means under such and such conditions, the 100 gram of this hydrogen gas will strike this 1 square centimeter of the wall in 1 second time. Now I am coming a very interesting aspect of this expression of mu. You know, every solid or liquid will have its vapor pressure at a given temperature. If the vapor remains in contact with this liquid or metal, liquid or solid, in contact with this liquid or solid at a given temperature, its saturation vapor pressure will also remain constant. And if we consider this metals whose vapor pressure is very, very small and could not be determined by any manometer or micro pressure meter. In this case, Knudsen diffusion method, Knudsen actually Knudsen diffusion method process will help by the use of this formula to determine the vapor pressure of any solid or metal. Suppose here this is called the Knudsen method, and Knudsen method is here. Suppose one container. Here is one container, and container. Here some metal, beryllium metal. Some beryllium metal have been kept within this vessel. Vessel taken as spherical as our design, or we can take another sort of shape. So this temperature, this vessel have been kept at temperature equal to 1457 Kelvin. 57 Kelvin. At this temperature, this beryllium, some parts of this beryllium will be vaporized. And here this vapor or the gaseous beryllium atoms are containing this vessel. So this vapor remains in contact with this beryllium at this temperature. So vapor pressure of this beryllium at this temperature is fixed. You can see the Andrews curve in case of vapor pressure, saturated vapor pressure of this liquid. The saturated vapor pressure of a liquid or any solid is fixed at a given temperature. If the temperature is changed, this vapor pressure, saturated vapor pressure will also be changed. With the rising temperature, vapor pressure will also increase and can be calculated by the use of the Clausius-Clapeyron equation. Here the temperature is fixed at this one. We like to see what will be the vapor pressure of this beryllium atom vapor. We keep here one small hole, within the container. The hole is very small, and the hole is smaller than the mean free path of this beryllium atom vapor. Otherwise, there will be interatomic collisions. And here this bulb is kept in vacuum. Outside of this bulb is vacuum. So this beryllium atom vapor will strike this hole and it will go straight. As there will be no collisions within this hole, as this diameter of this hole is much less than mean free path of this beryllium atom vapor. So suppose this has been kept for a period of time. Time is 60.1 minute. The experiment is done for 60.1 minute time, and then the experiment has been stopped. There will be weight loss, but whenever the beryllium vapors are coming out, the vapor pressure of this beryllium atom vapor will remain fixed at this temperature. As more gas is beryllium atom is escaping, the more and more beryllium metal atom is vaporized to keep the vapor pressure fixed. So here, suppose within this time, the loss of mass of the vessel equal to loss of mass of the vessel due to escaping the beryllium atoms from the hole at a temperature this one is 9.54 into this one milligram. This one is milligram. There is a loss of mass of this vessel due to escaping of this beryllium atoms is 9.54 milligram. All this data have been given. We have to calculate the vapor pressure. This equation has to be modified. This mu equal to 1/4 into rho PV equal to A naught T, and this is equal to WRT by N. W by M equal to N. So P into M equal to W by V into R, and W by V is the mu. W by V is the rho. So instead of this rho, we can write P into V equal to P into V equal to rho into RT. So rho equal to P, only P into M. Rho equal to this rho. This one is equal to rho into RT. So rho equal to P into M divided by RT. We can put here this P into M divided by RT into, now the C bar equal to root over of 8 RT by pi A. So this could be written as, here P is coming out into root over of 1 by 16, and here the into M square divided by RT square into 8 RT by pi A, or this one equal to P into root over of, this one is 2, 1 M cancels, RT, 1 RT cancels, so it is M by 2 pi RT. So mu can be expressed as P into root over of M by twice pi RT. Now let us do the calculations. So P the vapor pressure, here it is vacuum. P is the vapor pressure of this beryllium vapor, and P equal to mu into root over of twice pi RT by capital A. We can put all this data. Mu means mass of this gas striking, here escaping, per unit area, per unit time. So here mu equal to, that is a loss 9.54 milligram, means 10 to the power 3 gram, and divide by this per unit area. Per unit area means pi means pi into r square. Area equal to area of the hole equal to pi, and this diameter is given as Diameter is given as diameter is given 0.318 0.318 by 2 whole square. This centimeter into whole square. This is the diameter. Diameter by 2 is radius pi r square. And this value comes up. This value becomes 0.07 0.0794 centimeter square. So here we can write 0.9074 centimeter square. This is the area. So whenever this one is divided by area, it will give you the mass escaping in unit area. And the time is 60.1 into 60 second into, this is mu, and this one actually 2 into 3.14 into, here r in 8.31 into 10 to the power 7 r mole inverse Kelvin inverse into 298 Kelvin divided by mass of this beryllium is 9.01 gram mole inverse. So if we do these calculations, then this will give you 3.333 into 10 to the power minus 5 gram centimeter inverse 2 and into 290.501 centimeter second inverse. So if we calculate this one, we get 9.682 centimeter inverse 2. That means the pressure is found to be vapor pressure of beryllium, vapor pressure of this beryllium is found to be 9.682 centimeter inverse 2. If we like to express it in atmosphere, then it will be 9.682 and divided by 76 into 13.6 into 981 atmosphere equal to 9.54 into 10 to the power minus 6 atmosphere. 9.54 into 10 to the power minus 6 atmosphere. These calculations for the viewers are requested to do by yourself, and whether it is matching out or not, you can see. So by this way, in Knudsen process, the vapor pressure of this metal, which is very, very small, could also be determined very efficiently. Another important applications is also there. Actually, the rate of diffusion, Graham's law, rate of diffusion. And it is very easy. You can consult my note given in my channel under the head of About Kinetic Theory and Gaseous State. and in this case the rate of diffusion would be expressed as 1 by root over of A. This is also another application, verifications of this, of the Graham's law of diffusion. So this is all about today's lecture. In my next class, I try to explain the frequency of intermolecular collisions. It means this is number of collisions made by the molecules in unit volume, as it is the three-dimensional space, unit volume in unit time at a given temperature pressure of this gas. And henceforth also we shall discuss the mean free path, etc. So thank you all who are watching this video.